Morning, guys. Sorry for the glitch yesterday. Apparently, YouTube wasn't allowing any uploads. Anyway, I'll get this lecture up and running, and we'll continue through the weekend. It's best to do this in sort of blocks of 15 minutes, which makes it easier for me to upload to email and then upload to YouTube. So anyway, bear with me, and perhaps we'll find a time next week to at least convene by Zoom, just so we can chat. If nothing more, just chat about the situation and get some feedback from you guys. Anyway, here we are. You will recall that for a parallel plate scenario, which now we've discussed numerous times, plate separation D, voltage across, this capacitor is V. We know that's now established by a battery, that we can define the capacitance to be the charge stored on a plate divided by the voltage required to store that charge. So that's a definition. You'll remember that the units on this are in farads. It's been so long since we've been together that I feel we need a couple minutes of review. You'll also recall that the electric field is homogeneous between the plates of the capacitor. It's the electric field. And we derived in class that knowing that the electric field is equal to sigma over epsilon naught, we were able to derive that the capacitance can be described for a parallel plate only as epsilon naught, the plate area over the plate separation. Now remember, this is only good for a parallel plate, arrangement. So what I want to do is one derivation for you, and it's rather complicated, but we'll go through it, and then I'll give you solutions for another calculation, and then we'll arrive at some general conclusions. So you'll notice here that the units are important. So remember, epsilon naught is equal to 8.85 times 10 to the negative 12 farads per meter. And you'll see from the above equation that A over D has units of meters. So then, just from a unit analysis of this is going to be then farads per meter times meters, or farads. And that's exactly what we want. So just remember that theme is going to prevail here. So what I'd like to do here is, what happens if we try to derive the capacitance for other configurations? So, for instance, for a coaxial cylinders. So picture-wise, then we're looking at an inner conductor, and then we're looking at an outer conductor. And the inner conductor is going to be positively charged, and the outer conductor will be negatively charged. So you can imagine that this is not unlike parallel plate, except that this is kind of a rolled a rolled situation, right? So the inner conductor is positive, the outer conductor is negative. And if I were to draw that this way, so here's the inner conductor, right? Here's the outer conductor, and so this is going to be radius A, and this will be radius B. Okay, and again, the inner conductor is positively charged. The outer conductor is negatively charged. Okay, and we can ask the question then is what is the capacitance? What is the capacitance of this coaxial cylinder arrangement? So let's begin to address that. So we can talk about a relevant length of that coaxial arrangement. And so let's just write that down. So this is, coaxial conductors. Okay, so so a couple of things. I'm going to redraw this other picture here several times. So here's positive, here's negative. Now, what do you think the electric field looks like between those two? Well, the electric field then is going to look like this, right? So it's going to be emanating out from the positively charged entities and ending on the negatively charged entities. And let me just erase this since I kind of buggered that up. So there we go. I'm getting to learn how to use my iPad here. And not as good as a chalkboard and a piece of chalk, but we'll make do. So here's the electric field between those two. Now imagine that we can draw a Gaussian surface, right? So this is a Gaussian surface. Now you're going to have to recall the kinds of things that we've done back in the chapter on Gauss's law. And so you'll remember, I hope, and if not, you'll have to go back and review your notes. So remember Gauss's law, that the integral around some surface, and then this is a Gaussian surface, right? The electric field dot product into the area element is going to be equal to the charge enclosed by that area. Charge enclosed by the area divided by epsilon naught. Okay, so again, if we were to come back up here, and what does that Gaussian surface look like? Now it looks like this inside this coaxial arrangement. And then this is going to be some distance r in general, okay? And so we want to know what the electric field is at some point r away. Then whatever it is, it's going to be constant along this distance, right? It's going to be pointing outwards. And if you remember, the little patch of area here is going to have a vector which is going to be parallel to the electric field. So what happens to this dot product then is that E is constant, so it comes outside of the integral. And so this then is just going to be the area element of a cylinder. And again, you might have to go back and review that in your notes. And so the area, the relevant area of that cylinder is just going to be 2 pi r, right, the circumference of that red dotted line, times the length. Okay, and that's going to be then Q enclosed divided by epsilon naught. Okay, so so then in general then Q enclosed is going to be epsilon naught times E times 2 pi r times L. And again, let me get rid of this and make that a little bit cleaner. So that's going to be pi. There we go. Okay. And likewise, the electric field at that distance r from inside from the positive conductor is going to be Q enclosed by that Gaussian surface divided by 2 pi epsilon 0 L times r. Okay, beautiful. All right. Now, we have to go back and review some things from chapter 24. So from chapter 24, we remembered when we looked at the electric potential for point charges that we used an equation that was V final minus V initial was equal to the negative integral of the electric field dot ds. Okay. Now, this is going to go from some initial to some final position. Typically, this is to the positive plate, right, to the positive side. This is from the negative side. Okay. And if you look up, and I'm going to redraw it here. So here's our coaxial arrangement. All right, positive and negative conductors. Now this is a cross section, right? You realize that it's a very long concentric cylinder. That the electric field is in this direction, but you're integrating from the negative side to the positive side, and so ds, right, ds is going from the negative plate to the positive plate, so that E dot ds is actually going to be the magnitude of E, magnitude of ds, times the cosine of the smallest angle between them, but that's 180 degrees. So that's actually -1. So then that's just going to be negative E ds. So then what happens to that integral from up here then is that we get then V final minus V initial is going to be negative initial to final. This then is going to be negative E ds. And so then you get V final minus V initial is equal to then the integral positive, right, final to initial E dot ds. Right, usually V initial is at 0 volts. And so in this case, this is going to be V initial, and so then V final, which then is going to be V, is going to be the integral from VI to V final E ds. V initial is the negative side, and so what your book does is say that V final, which is V, is equal to the integral from the negative plate to the positive plate, E ds, where ds is the length element going from the negative cylinder to the positive cylinder. We're going to stop there, okay, and then I'll upload this, and then I'll move on to part 2. Okay, see you guys in a bit.